Minutes to let everyone hop into the Zoom here. Awesome. Okay, looks like we have folks joining in. So maybe we can get started here. So today's we have a really cool version of the community paper reading because we actually have the paper authors joining us. So we'll actually get to ask all the questions that we have at the end of the paper to the authors directly. So really excited to welcome both Xuefei and Zinan, who are the authors of the Skeleton of Thought, Large Language Models Can Do Parallel Decoding paper. The link to the paper is linked in the webinar, so you can go ahead and take a look at it. But welcome. Thank you so much for joining us. Xuefei, do you want to maybe kick us off with an introduction of yourself?
Okay, nice to meet you. Yeah, I'm Xuefei Ning. I'm from Tsinghua University. I'm now a postdoctoral researcher. Yeah, and Zinan is a friend of me in my undergraduate, during my undergraduate time. Yeah. Awesome. So we usually talk about like doing research work together, and this is by chance we together do this work.
Awesome. Zinan, do you mind introducing yourself?
Yeah, so thanks very much for inviting us, and we're very excited to be here. Yeah, so my name is Zinan. So I recently graduated from Carnegie Mellon University, and I'm now a senior researcher at Microsoft Research, based on Redmond, Washington. Yeah, and yeah, we have, as Xuefei said, we have been friends for a long time, and we think about those AGI, etc., together, and then come up with this work. So yeah, very excited to be here to share this work.
Awesome. Well, I gotta ask, how did you guys come up with first of all, really cool title, but how did you guys come up with the idea of the paper? Like, how did that start?
Yeah, actually, the idea originates from our user experience of ChatGPT. Usually, I want to find some key points and expanding on that key points when I'm using ChatGPT. And if I don't see the key point I want, I actually want to rephrase my question. But I have to wait for ChatGPT to output each word one by one. And actually, for many questions I ask, for example, I'm like looking for some knowledge and some inspirations. It often gives me many points, and usually there are not such close relation between these points. And it's a very intuitive question. So that why can't ChatGPT like parallelly give these points out for me, and it will be much faster. And also, my research field is on efficiency, and I think this is like a new perspective on improving the efficiency. So I discussed with Zinan, and Zinan has some like really good ideas on how to make this work using prompting. So we start on this work after the discussion.
Got it. Wow, that's a really got it. So from your own usage of ChatGPT is kind of what inspired this. Also, yeah, just want to also introduce Sally Ann on the call. Sally Ann, also be, doing the paper reading and asking, our guest today a bunch of questions. So yes, Sally Ann, go ahead if you have anything you want to jump in with.
Yeah, I think like really where I want to start is kind of just diving in. I'd love to give like an overview of the paper, really understanding like what the key thesis is here, what your findings are. So I'd love for you guys to just jump in and take that away.
Okay, so I'll share my screen, I think.
Yeah.
Okay, I think I will use this website and I'll work to go through the key ideas. Can you see the screen of the website?
Yep.
Okay. Yeah, our work actually aims at decreasing the end-to-end generation latency of LLMs. So one of the major causes of the high generation latency, the sequential decoding approach, actually this aspect is not tackled that much in the efficiency literature. And this work, motivated by the thinking and writing process of humans, we propose this skeleton of thought. Skeleton of thought first guides the LM itself to first generate a skeleton of the answer and then conducts parallel API call or batch decoding to complete the content of each skeleton point. Not only does SOT provide a considerable speed up as we expected, but it also can potentially improve the answer quality from several aspects, in particular diversity and relevance. And we regard SOT as an initial attempt at data-centric optimization for efficiency, and in particular inference efficiency. We have currently not found much efforts towards this direction. And also we reveal some potential pushing to think and write more like a human in a more strategical and organized way for answer quality. Yeah, there is some background numbers is to reveal how the LLM generation process is slow. For example, for API-based model, it can take 22 seconds to answer the question in our illustrated figure, and 43 seconds for 33B model run locally on our one of our A100 GPU. Yeah, and we actually analyze three major algorithmic causes of slow inference. The first one is caused by the model size. The model size leads to large memory consumption, large memory access, and large computation workloads. And these all induce non-latency, low throughput. And the second one can be same as brought by the special attention operator in the transformer architecture, and many work are targeting this problem. Because this attention operation has a quadratic memory and a computation complexity. And this is especially important in training or the generation of non-sequence. And the third reason is that currently almost all the LLMs decode decode the words one by one, generate token one by one. And yeah, there are some work that is targeting this problem, but they're targeting it from a different way. But generally speaking, the most of the literature has been addressing the first two axes by compressing and redesigning the model or redesigning the serving system and hardware. So we ask a question: is that can we accelerate off-the-shelf LLMs no matter it is run locally or it is an API-based model without any changes to their model, to their system or hardware? So in this work, we rely on data-centric method to prompt the LLM to be faster. And actually our method is very straightforward. We have two stages. The first stage is the skeleton stage, in which we query the LLM to first list out a skeleton in very shortly, and where each skeleton point usually only have 3 to 5 words. And after it lists out the skeleton, in this second stage, we call point expanding stage, we let the LLM to parallelly decode the contents for each point of the skeleton. And for local models, we just batch the decoding together, and this will accelerate the decoding much. And for API-based models, we will issue parallel API calls to the API endpoints.
Hey, quick question. I'd love to like stop here on this diagram. I think it's super helpful for understanding the method here. And you touched on it a little bit, but can you explain to us all where the kind of inspiration was to come up with this method of sending in the prompts this way?
Oh, okay. Actually, the inspirations comes from how we humans think about this problem. When we encounter a question, no matter this is a single question or a complex task, we usually first establish a skeleton of how we can answer to this question. Let's just think about when we are taking a test. Now, when we are taking test, we know there is a like well-established protocol of how we can reply to this question to get a high score. So we just like write down the protocol, and then we search in our mind that what's the knowledge to like add to each point of the skeleton. So we like based on this insight, we just designed to first prompt the LM to make itself behave like an organizer. He should organize the answer of the overall question, and then in the next stage, each you can see like each LM is only responsible for adding the contents and details of one point. Yeah, actually this is very straightforward, and we just like think about how we human do this work. We just ask ourselves what's the skeleton, and then we find the knowledge needed to add it to each point.
Yeah, that's awesome. I think that it helps have that context because it makes so much sense. Like when I read that, when I was reading the paper, first thing I wrote down was like super cool. And then the second thought was like, it just makes sense to think about it in this way. Like that is what we're doing. We're breaking it down. And we should try to mimic it. I think that's a secret there. So awesome. Thanks for explaining that.
Thank you for the question. Yeah, my English is not so good, so I think this really helps me to expand on the details of our method. I think actually on our website we did not write the prompt template, but the prompt template is given in our paper. So actually I have already finished the go through of our method, and then the section is the results section. We test 11 models, and 9 is open source models that we run locally on our 3090 GPU and A100 GPU, and two API-based model. Yeah, and this is the summary of our results. And the x-axis shows the speed up, and the y-axis shows the net win rates with respect to the sequential decoding approach. Yeah, and we can see that almost all models can achieve a speed up with SOT, but many models can achieve a higher relevance and diversity for the answer quality than the sequential decoding baseline. This is like a very brief overview of our results, and this is a demonstration which like echoes the very first motivation of our study. We can after SOT is used, we can see the point is decoding parallelly. We at first we can know what's the point it want to give us, and if I cannot find the key point I'm interested in, I will just stop generation, like rephrase my question, or when I find the inspiration that maybe time management skills I haven't I haven't known that. I will just like stop the generation and say, oh, okay, I'm not caring about other points. I just want to know the time management technique. Please give me more information. Yeah, I think this is like a simple demonstration that can echo the very first motivation. Okay, and finally, on this website, we pasted the limitation and the prospects discussion on our paper here. SOT, we regard SOT as a very conceptually like reasonable and maybe useful thing, but it kind of solution is not very general for different question types. Especially it cannot answer math and code questions well. This is actually reasonable. Before we start to implement SOT, we have like anticipated it will not be very good at math and code problem because it is somehow contradictory with COT. Because COT actually relies on the expanded details of each step to give a better reasoning, better results. While SOT hopes to statistically list out a skeleton in advance before all the details come out. So this is somehow contradictory. And more broadly, SOT is suitable for the questions with a clear answer structure that can be planned in advance. For example, when you take a test, when you like give consultory, and when you give some knowledge or ideas, this kind of questions. So in order to use SOT for general questions, all the types of questions, what we are thinking is that we can design a pipeline to only trigger the SOT mode for question types and descriptions that are suitable for SOT. Or for example, an active case will be that when the user requires a very short answer, like by just saying hi, or by formulating a multi-choice question, or by explicitly say that please give me an answer in 2 words. So we should not trigger SOT. And also math and coding problem, we should not trigger SOT too. In that case, we should trigger the like sequential generation mode and use as COT or that kind of things. And the second future work.
Oh, sorry. Yeah, quick question. Before maybe we go into the quality of the answers, I think we had one question. I think Zinan may have already answered it, but could we jump back to just how the demo was super cool. So it looked like it was almost 2 times as fast by using the skeleton of thought versus the previous. How could you maybe walk through how are you guys defining this? What models did you see the biggest speed up in? What types of questions did you see the biggest speed up in?
Oh, okay. I think this detailed answer is actually in our paper. Actually, for bigger models, we can get a larger speed up. For example, in the Vicuna. But this is not a universal conclusion, because many aspects will influence the speed up. For example, how long is the sequence it will generate, both in the sequential mode or in the SOT mode. But if we only think from the hardware aspect, like a larger model maybe can benefit more from this SOT process. And why is that? This is because that a larger model is usually more bottlenecked by the weight loading in the decoding process. So because it has more weights and the decoding is totally bounded by the weight loading from the GPU HBM onto the GPU chip. And so popular work such as flash attention, it cannot help much because it cannot help with the weight loading. But our SOT work, it batches the decoding of the points, and especially for large models, it can has a like considerable speed up. And I think maybe looking at the models that provide the least speed up will be somehow more clear to demonstrate to explain how in which cases our method can speed up the generation. We cannot speed up stable VTuna. This is because stable VTuna cannot follow our point expanding prompts. And we say that you just, in which we say that you just expand on this point very shortly, do not expand other point. But we find that stable VTuna cannot always follow this instruction. So it will, like for each point, it will output a very long sequence. And this sequence length will match the overall sequential decoding length, so it cannot get a speed up. So as long as our model can follow the instruction well and it's bounded by the weight loading in the decoding stage, it should get a good speed up.
Got it.
Yeah,
Wow.
and there is also a analyze on which types of questions we can get a better speed up. And the green one marks the marks the question types that SOT can get a good answer quality on, and while the red one is the question types that the current SOT solution cannot get a good answer quality. And we can see that on the common sense knowledge generic, which we intuitively think SOT is suitable for, it can indeed get a very good average speed up on all the models between all these concrete questions. So at least I think SOT is very useful for these types of questions if we can trigger it at the correct time.
Okay. Got it. And actually, I think someone in the chat had a question on that. Arize asked, in the case where you can parallelize, how do you at the end combine all the responses? Are you guys using any chains or agentic approaches, or yeah, how are you doing that?
Yeah, this is a very good question, because actually we only concat them together. It's a very simple method. Yeah, but we have been discussing on this many times. So because intuitively for some question types, this concatenation is not that suitable, especially for the coherence of the answer. Yeah, but as SOT main aim is at the decreasing the latency. If we use another model to combine the all these contents and then we decode one by one, it cannot get a good speed up. But we can use a smaller model to do the combination. Maybe the expert has already write all the content. You just need to aggregate all this information, and maybe the output process of the aggregation process can be parallelized by token. It can prefill all the tokens together and output some tokens together. Maybe that's possible, but we actually haven't tried the thing ourselves. That's only our image. Our prospect of how it can be done, for improving the coherence.
Yeah, the other approach we were thinking about is that instead of having another step at the end for concatenating all the answers, like using another model or other ways, the other way is that during the outline skeleton stage, when the model output the skeleton, not only output the skeleton but also output how we should concatenate the answers in the end. So if you look at the papers, we show some results. So currently what we're doing is that we, for each point, we first put a skeleton point and then the expanded answer, and then the second skeleton point and the expanded answer. And if you look at it doesn't look that well for for some type of questions like emails. So for emails, people usually just directly write the content. We don't have 1, 2, 3, 4, 5, right? So So this is something like we're thinking like during the skeleton stage, the model have the information like how we should concatenate the answer in the end, like whether we should put a skeleton point in as a part of answer or we should remove them. So the other way we're thinking is in the skeleton stage, we not only prompt the model to output the skeleton, but also indicate to us how we should concatenate the answer in the end, or how should we post-process them. And then like in the end, we just directly do whatever like the language model suggests us to do, so that we don't need to have another process in the end, which will increase the latency. And also, and also it's more natural to, if we think about how humans think, like when we like people ask us to write an email, we directly know that we don't need to put like 1, 2, 3, 4, 5 in the answer. We know we just directly write the answer. So it's also closer to how humans think.
Got it. And
actually, we have tried the solution that Zinan just mentioned, and it works well for the API-based commercial models, and works not that good for the open source model. So we just do not include this trial in our paper currently.
Yeah. So it's like for because the prompt will be more complicated, and like for powerful models, they especially those closed source model, they are able to understand it and then give very good results. But for open source, it's currently challenging to make them understand like, yeah, those kind of requests.
could you walk maybe us through, the first pass reading the paper? The examples, like you said, common, general knowledge made sense, but I kept wondering, how does it work for math, right? For sequential. Could you walk through like where does it go wrong? Does it, I don't know, in the concatenation step, you don't need any of the parallelization steps? Like, yeah, maybe some common, what have you guys noticed in the common pitfalls for math or Fermi type questions or coding?
Yeah, actually, current SOT cannot answer math questions well. It's because of what you just said. Do not have the context, and maybe Zinan can add more information on the concrete analysis of the math question.
Yeah, sure. So yeah, so basically like yeah, I can mention firstly like high level why math is kind of challenging for SOT, and then we can look into those examples to understand why. So like basically for math, like as many paper previously, like a chain of thought and many other papers point out, for math question, in order to understand correctly, it's very important to ask the language model to think step by step. It's also how humans think about math question. We think step by step. But in skeleton of thought, we basically request the language models to first come up with the outline, which is kind of like skipping the computation details and directly jumping to the conclusion, like the answer should contain several steps. And then we fill in the details without referring to the previous results, which is very hard, I mean, to make the answers correct. And it's also counterintuitive about like how humans think about math questions. Yeah, and if we go into the technical details, so the two key challenges of applying skeleton of thought in math questions is that firstly, we need to come up with the skeleton very well. And secondly, like we need to fill in the detailed computation step for each skeleton point without referring to the previous result. And what we see like in these experiments is that for very strong models like ChatGPT, they are able to come up with a reasonable skeleton. So for example, we can look at the examples below. Yeah, so this one. So the question here is like solve for x in the equation 3x plus 10 something, yeah, etc. So this skeleton of thought like show at the upper blocks. So the orange part is the skeleton. So if we really look at the skeleton, like you mentioned, like which steps we need to do, those steps are actually correct. So it's able to like understand like what steps we need to take. But if you look at the detailed expanded answer for each skeleton point, which is in the black color, we will see that it starts making mistakes from the second step. So basically here, like this can be done by subtracting 5x minus 10 from both sides this step. Like, yeah, we don't need to follow math, but the takeaway is that this step is already incorrect. And it's very reasonable because when we expand the point, we are expanding the detail point for point 1 and point 2 independently. So basically when the model try to fill in the details for the second point, it doesn't know the result from the first point. But like in math, we need to know the previous result in order to deduce the second one. So that's why it makes mistakes. And this is for strong model, but if we look at a weak model, those orange skeleton is it's even harder to it's even hard for them to make the skeleton correct. So for example, if we look at the same problem, but if we use the Vicuna 13 billion model, the third step, it says apply FOIL, which is incorrect. Like we don't need to do it for this step. So the skeleton point is incorrect. Then then it's even harder to get a complete answer correct. So yeah, so these are why a skeletal sort is not suitable for math questions. And in more general, any questions that require step-by-step reasoning, it's hard to apply skeletal sort.
Awesome. Thanks for walking us through that. I guess it makes sense, like you said, that it struggles with creating the actual details because it's lacking the context from point 1, and it can't multiply what it doesn't know to multiply, things like that. So that makes a lot of sense. But it got me thinking, do you see a future where we have a specialized skeleton of thought for these types of questions, and what might that even look like?
Yeah. Actually, we have prospect or some solution in the near future, also in the some solution in the remote future. In the near future, we think we can trigger SOT only for the questions it is suitable for. And how can we trigger it? We can use another small model to do this work for us, or we can fine-tune the LLM to output a special token to indicate whether it should trigger the second stage. Because there is a very interesting phenomenon in our work, is that in some cases some strong models can only output the skeleton stage when it encounters the math question, and it will output nothing in the point expanding stage, and it will get math question well. But not this is a very rare case if the model is not tuned. But we think that after some fine tune, more models can understand if this question I should output all the answer in the sequential manner in the skeleton stage, and just skip the point expanding stage. I think fine-tune will bring this capability. We believe this, and also in the long term, we think maybe the scatter sort and together with the chamber sort, we should generalize all these things into a graph of sort, because our human actually do not think all parallelly or sequentially. It's a more complex graph, and also it should be dynamic, because we cannot plan all these important points in advance. But after some details is out, we come up with another idea, find a new connection, and then we add another point that we will expand later. So this is a very is a far plan, I think.
Sure.
Maybe have some discussion to add to this. Okay.
Yeah, that all sounds amazing. I'll look forward to some of that future work. it makes sense too, especially the graph of thought, again, you know, mimicking what our brains do, right? It's a little less orderly, it needs to be a little bit more dynamic. So we'll be really interested to see the results of that following close along. You did mention something else though that got me thinking, and answering that. You were saying that maybe we could fine tune these LLMs to choose specific or when to use the skeleton of thought or when to not. But then you also talked about, you know, using this without optimizations, but I was curious what your thoughts are on combining, you know, the skeleton of thought with other optimization techniques. We've talked about LoRa here before. So what are your thoughts on that?
Yeah, we have got that question in advance. If actually LoRa helps many with like training stage, it will be more parameter efficient training. So if we want to tune the models to be more SOT capable, so we can use the LoRa optimization to like to fine tune our model faster. And we actually do not think more on how to combine a training time optimization like LoRa and purely inference time optimization like SOT further. But some people has mentioned to me that he want to like adapt it as the like idea of SOT into accelerating the training stage. But actually, I do not know how that can be done. So it will be interesting to think about, but I have not think it through.
Yeah, absolutely. It's definitely interesting because we're seeing what I'm experiencing at least is there's a lot of optimization, but there's definitely people working on different pieces of the puzzle. And I think something that's really exciting is we'll get to see how these pieces can work together and what results those bring. So I think it's really exciting to see. I have just a few more questions for you, if you don't mind here. So another thing that we touched on, or we didn't maybe touch on too much, was the fact that there seems to be weaker models in this and stronger models. And there were two models that you mentioned as weaker in this context, and that was OpenChat 13b and Vicuna 7b. Any ideas why they're weaker in this context? Is it something to do with their architecture, or what do you think makes them different?
No, I think it's Ning can answer this question. Because
yeah, so those like OpenChat, Vicuna 7 billion. So they are all based on like a Llama model. So their architecture are the same, but the difference is that like when they do the instruction fine tuning, they're using different ways. And what we see like why they perform not that well like with SOT is because like their ability to understand the SOT instructions is kind of weak. So basically, like for example, we Xuefei mentioned one example for another model, but basically, like the model need to have some basic instruction understanding capability to understand, like we're asking it for the outline, or like we're asking it to only expand the one outline. If it doesn't understand those kind of things well, then the SOT answer will be a mess. So what we see is that for those two models, like their capability of instruction understanding might not be that good enough to use with SOT.
Gotcha. That makes a lot of sense there. I had a hunch that there was something that those two models did a little bit differently, because it makes sense, right? How could they have such poor performance compared to some of the other ones? All right, I got one more question for you all before I let Aparna get in with some of her questions here. This is one that's been on my mind a lot as I read all these different papers. There seems to be kind of one thing that keeps being brought up, and so we mentioned being in this data-centric era of machine learning, but it seems like in all these papers I'm reading, there's more and more evidence that the transformer architecture, and more specifically the attention mechanism, is not that helpful. It actually is hindering us in a lot of ways. So do you see a shift back into this kind of more model-centric paradigm where we're looking to replace that attention mechanism? Do you see that in the future?
Yeah, actually, Zinan and I have discussed a lot on this type of questions. What is the next architecture towards like AGI? And so we haven't started our investigation into this yet. Our very personal opinion is that the current architecture is not the ultimate solution. We might need other architecture components at least to step further. For example, we are very curious whether we need some like new neural memory mechanism with learnable access interface and update strategy other than backpropagation and so on. Yeah, but this is a very personal opinion without any experiments. We just think this is needs more design in the future to step further into the AGI. Yeah.
One additional thing is like, so we both Xuefei and I, we definitely believe like in the future, like this transformer architecture is definitely not the end. Like we need something new. But that's kind of like in a relatively longer future. But what currently people see at the current stage is that this transformer architecture, there's still a lot of potential that we haven't fully explored it yet. And that's why like there are a lot of papers coming out saying like we just use transformer architecture, and we just by doing a little bit more data engineering, we are able to get much better performance. So this is many people are currently investigating. So we think that if we look back in the history of machine learning, it's always like alternating between like data centric and the model centric and data centric. So every time new model comes out, there were like and there are a lot of potentials we can do. Like people do a lot of like data engineering to further boost the performance. Like if we look at back, like every time the CM comes out, ResNet comes out, now like this transformer architecture. But if we look at the longer horizon, then like there will definitely be a new model architecture come out that says that all the, I mean, like dramatically improve all the previous results, and then people start thinking back about like how to design better models. Yeah, so I think like if we go back to this question, I mean, in the short term, there's definitely a lot of more people can explore it, like based on transformer architecture and do more data engineering. And our work is kind of like the first trial of this direction for efficiency. So there's a relatively little work previous on that. But if we look like a longer into the future, then definitely, we agree we need better architectures. And some people are already exploring that. Yeah.
Okay, I'm noticing we have about a couple more minutes before we have to wrap up. So maybe I'll just ask one last question, and then thank you guys for joining us. I think we see a lot of folks actually trying to use LLMs or generative model, this architecture in production. Any application that you guys are, maybe more on the real world side, you guys think this could have big potential for, or any real world application you're motivated by?
Because the very first motivation comes from the general chatbot application. So I think SOT actually has the potential to be used in a general chatbot to improve the user experience, and also lower down the system cost, because like SOT actually introduced a new parallelism level. It can parallelize between segments of contents, and this actually brings some space for the system optimization. For some serving framework, it can choose to like more intelligently parallelize between the segments of one question, or even multiple questions, multiple users, and it will like help lower down the system cost, improve user experience, and so on. I think this is the general chatbot system is my is the application that I care about.
Yep, the original motivation. Got it. Got it. Cool. Well, I think we're at time right now, so just want to say big thank you, Xuefei, Zinan, for joining us today and going over this really outstanding paper, and wishing you both the best of luck on the future work, and we'll be following along what you guys do.
Thank you very much for inviting us.
Thank you.
Thank you so much. Thanks everyone.
Thanks everyone.